Some seconds. Yes, we are live at YouTube today in a very good morning. So, good morning, everyone. Good morning, Professor Ketu Popat.
Good
Uh,
morning.
I'll, I'll read here a short biography of Professor Ketu, and then I'll let him free to give her his presentation. Okay, thank you very much. Thank you again, Ketu. Professor Ketu Popat is a professor in the Department of Mechanical Engineering, School of Biomedical Engineering, School of Advanced Materials Discovery at Colorado State University, USA. Okay, he's also the associate department head of mechanical engineering and director of undergraduate programs in biomedical engineering. Prior to that, he was working as a research specialist in the Department of Psychology at the University of California, San Francisco. He has authored over than 130 peer-reviewed publications in journals such as Langmois, San Francisco, Biomaterials, Journal of Orthopedic Research, Journal of Biomedical Materials Research, etc., and has an age index of 41. He has also presented his work at numerous national and international level conferences. He received his PhD in bioengineering from University of Illinois at Chicago in 2003. I think Ketu has fallen. We can wait him a bit. Okay. I'll continue here. I think we are all on YouTube. Let us see. Yes, we are alive. We still alive on YouTube. Don't worry. I'll only continue here just for you that are watching us here. So he received his PhD in bioengineering from University of Illinois at Chicago in 2003. Master in Chemical Engineering from Illinois Institute of Technology, Chicago. Okay, Ketu is changing his place because he's at the Material Research Congress in Foz do Iguaçu, and the internet signal is not too good there. So of course, we wait him, and I will finish here his short biography. He got his master degree in chemical engineering from Illinois Institute of Technology, Chicago, in 2000. And the bachelor's in chemical engineering from MS University in India in 1998. Okay. So he was invited by Professor Ana Paula, that is watching us here today also. And now we just wait him. He's here.
Back again.
Don't worry, you are here again. Hello, Anna.
Okay, sorry about that. I will share again.
Yes, don't worry. When you were changing the place, I just finished your biography.
That's
Read your biography.
okay. Can you see my
Yes, I have
screen now?
here your
Okay.
presentation.
I think outside the internet is more faster than inside, so I'm just
Oh,
outside.
yeah. Any problem, you can write me on WhatsApp. Feel
Sure.
free. Okay. I'll
Okay.
just disappear from your screen now.
Okay.
Okay. So feel free to proceed.
Okay.
Thank you again, Ketu.
Cool. Thank you. Thank you very much. For inviting me for this presentation. And thank you very much for the introduction. I am actually going to talk about some of the research that we are doing in my lab, specifically in the area of surface modification and surface modification for different types of materials that we can use for tissue engineering and medical device applications. I think one of the main theme in my lab is specifically focusing on hard materials. So we're actually working a lot on titanium and titanium alloys. We do a lot of different types of surface modifications. A lot of our surface modifications are actually at topographical level, which means we are trying to change the topography of a surface, but we are also trying to change. We're also trying to change the chemistry of a surface. So a lot of the work that I'm going to talk about is sort of combination of how we can change the topography and how we can change the chemistry of a surface, so we can use these surfaces for different types of tissue engineering applications. Um, I before I begin, I just want to give some acknowledgments to some of the funding for last. I've been a professor for almost 15 years now. I started in 2007, and over the years, my lab has received funding from many different agencies. I think a lot of the work that I'm going to talk about today is actually funded by NIH, National Institutes of Health. Um, and specific in the orthopedics area and specific in the cardiovascular area. I also want to acknowledge my students. As Professor Rafael introduced me, I am a faculty in mechanical engineering, but I'm also faculty in biomedical engineering and also the materials school. And so I have students from all these different departments that work in my lab. And so right now I have three PhD students, two master students. I actually have two visiting students from UNESCO who are in my lab in Colorado right now, Daniele and Leonardo. Daniele arrived in January of this year. Leonardo just arrived in August of this year. And then I have some bachelor students also. A lot of the work that I'm going to talk about is done by Roberta, who is also actually from Brazil, but she was not a Sandwich student. She just applied to our PhD program. Roberta did her PhD. She graduated in December, and now she's doing her postdoc at MIT in Boston. And I'm also going to talk some work which was done by these two other students that they graduated in the last 2 years. I also want to acknowledge my collaborators. I have a very strong collaboration with different faculty all across the world, but specifically from Brazil, Professor Ana Paula, who I have been collaborating for actually many years, 2010. So about 12 years I have been collaborating with Professor Ana Paula. Paulo Suarez from Curitiba, I have been collaborating for almost 10 years. Alessandro, 5 years. I have a lot of collaborations in India that I'm working with, South Africa, some in Europe, and also have a lot of collaborations with people in in the United States in our university as well. A lot of these collaborations, they have grown very organically, which means that I have had sandwich students in my lab, and then we have a project, and then there is a lot of exchange going on between faculty and students, and I think that has been very fruitful in terms of working on some really interesting research projects for last many years that I have been directing the lab. I think my background was already given, so I will not discuss more about my background. Thank you, Professor Rafael, for giving the background. I'm originally from India. I have been in the United States for 24 years now. I came to United States in '98 to do my master's, and then I did my PhD postdoc, and I have lived for many many years now in United States. Actually, more than half my life now I have lived in United States. um, and whenever I come to Brazil, I blend very well because I look like somebody from Brazil. I look like Brazilian, which is very interesting. That a lot of people in India, they look like people from Brazil. So it is very. When I come here, I blend in very easily, and I think this is my 10th or 11th time in Brazil right now. So I've been in Brazil many many times, and it is all because of my collaboration with Professor Ana Paula. I have been able to come and visit and know more about Brazil and know more about the research that's going on here. I am from Colorado State University. Colorado State University was founded in 1870. Like a lot of universities in the United States, it was an agricultural university. Then it became an agriculture and mechanical university, and then it became a university which has all different types of majors. We're actually located in the northern part of Colorado, in a town which is called Fort Collins, which is a very small town, about 150,000 population. We have about 24,000 undergraduate students, about 4,000 graduate students. We have a very big veterinary medicine school, and we have about 1,600 faculty. I'll just show the map and some pictures about where the university is. So this is one of the places in our campus. You can see in the summertime it's very nice and green, but in the wintertime we do get a lot of snow. So it does become very cold, and we have a lot of snow. And I always tell students that when they want to come and do sandwich PhD, don't worry about the snow because we have heaters everywhere in the rooms, in the cars, and everywhere. So you don't even feel like when it is so much cold. This is fall season, autumn season. Within maybe 1 week or 2 weeks now, in Colorado, we will have this season where all the leaves will fall down, and then the snow will start coming. This is one of the parts of our campus. As you can see, this is our library, and you can see a lot of students. This is our student center. This is a stadium for our football team, which is not the same football like here. It's American football. And the town itself is actually located, as I said, in the northern part of Colorado. We are actually about 100 kilometers north of Denver. So you come to Denver, which is a very big airport, and then you can take a bus, to go to Fort Collins. We are in the state of Colorado. So if you look at this area here, this is all flat. This is all Rocky Mountains. So a lot of snow, a lot of ski, a lot of hiking. Very natural area. This is just some pictures of the city of Fort Collins, just to give you an idea. We are a very small university town, where university is the main place where people come and study. Uh, and we can see the mountains from the campus. We have a lot of lakes on campus, so it is a very very beautiful place, to live and also to come and do research and to study. My lab is called Biomaterials Surface Micro Nano Engineering Lab. As I mentioned, we do a lot of surface modification of different types of materials. My lab is actually located in this building, which is a very interesting building. It is a building where we don't have our own labs. Everything is a shared lab. So we basically have lots of labs, and everyone can use everything that they want to. There is no like restriction in using. So it's a very collaborative lab. This is just some pictures of my lab. We do a lot of chemistry work. We do a lot of cell culture work. We do a lot of bacteria work. And so it's a very interdisciplinary building, because in the area that I have lab, there is faculty from chemical engineering, there is faculty from electrical engineering, faculty from chemistry department, all have labs in the same area, and all of us can use all our labs without any restriction, which is very good, because then we can have really strong collaborations with people in different areas. My lab mostly has focused on surfaces of biomaterials, and we have focused mostly on metallic implants. In past, we have actually worked with polymeric implants as well, or polymeric scaffolds as well. But our focus has been mostly how we can actually improve the performance of these kind of medical devices. Our goal in the past 10 or years so has been how can we take knee implant, hip implant, screws which are used for dental application, how we can change the surface properties so that when these implants are actually put into the body, then they have a good integration with the tissue and we don't have any failure. Now, as you know, metals are very commonly used. Here are some examples of metals and alloys. You have the knee implant, you have the stent, you have the screws, hip implant. There's a lot of polymers which are also used, such as vascular grafts or scaffolds for tissue repair. As a matter of fact, implants are very, very commonly used. Maybe about 10 to 12% of the total population in the world actually has implants. So it's a very, very big area. And one of the most important aspect about all these materials is the surface, because surface is the first thing that comes in contact with the body. As soon as you put a material inside the body, the surface comes in contact. And as soon as the surface comes in contact, we have a lot of things that happen on the surface. Like, for example, in this case, you would see that there is proteins absorbing, then you have platelets absorbed, then you have blood clot that can happen. And if you have all the wrong kind of implants, wrong kind of proteins that absorb on the surface, these implants would start the rejection cascade. These implants would then eventually get rejected, which would be really, really bad, because then these implants will have to be removed. And so our goal in my lab has been how we can control the surface properties of these implants so that you are actually able to have the right kind of interactions happen on the surface. We have the right kind of proteins, we have right kind of cells that come, and then we have the integration of the surface that happens. And so our goal is a lot on how we can engineer the surfaces so that the interactions between the cells and the surface is in a very controlled way. We try to take inspiration from natural tissues. So you have a material that is going to come in contact with tissues. I think it's very important for us to know what the properties of the tissues are, so we can design the material surface so that they have a good interaction. And so we always think about tissues, and we always try to study what kind of properties the tissues have. So when you think about tissues, tissues are cells and everything which is not the cells. Everything which is not the cells is called the extracellular matrix, and cells are the ones that live in the extracellular matrix. Cells are the ones that actually make extracellular matrix, and cells plus ECM is the tissue. But when you start thinking about the components in which the tissue is built, the extracellular matrix actually has a lot of interesting features. It is made up of biomolecules. So you do have biomolecules which are in the ECM, but these biomolecules have different kind of properties, such as some of these are fibers, some of these are large molecules, some of these long molecules. They are all arranged in a certain way. That is what gives tissue the mechanical properties. But then you also have cells which are in this extracellular matrix. So the cells are using these biomolecules to be able to do their function. And so by doing such kind of analysis, we can now figure out what are the kind of properties that we need in the materials. Materials need to have similar structural properties that of the ECM. But materials also need to have biomolecular properties so the cells can interact with that material in an appropriate way. And eventually you have the integration that is actually going to happen. So with that idea, we have tried to focus quite a bit on titanium. I always tell everyone that titanium has been our favorite metal for many, many years, because we have worked for so many years in titanium. We don't really work more on the bulk properties of titanium. So for example, we don't really make titanium alloys. I rely on collaborators like Professor Anna Paula to help us making better alloys. I think we focus more on the biological interaction of materials with uh, with cells, and we have used titanium based materials for many different types of applications. So for example, right now one of the projects that we work on is on stents, how we can make stents so that they don't clot the blood. But titanium is used for stents, it's used for knee implants, dental implants, a lot of different applications titanium is used for. I won't talk a lot of detail about why titanium is important, but it has some really good properties so that it's biocompatible for all these different type of applications. Orthopedic implants is a very big part of where titanium and its alloys are used. As a matter of fact, orthopedic implants are very common as people grow older. I know so many people in my family who have knee implants. And as you grow older, your joints are going to not work, so the doctor would recommend you get a knee implant, and the knee implant essentially is made up of titanium alloys. And it is expected that people, as we are living longer, we will need more and more orthopedic implants so that we can still be functional, walk, and all these things. The two main big type of implants, which are orthopedic implants, are the hip implant and the knee implant. But there are a lot of smaller implants as well, such as plates and screws and all these different kind of things, which are also made from titanium. Typically, when you take these titanium implants, right now or in past, the way they used to be implanted was you would actually remove the bone marrow and you would put the titanium implant into the bone and you would put some type of a bone cement. But for many years, we're not using the bone cement because when you have a bone cement, you have this area where you can have failure that can happen. And then if you have the rubbing of the implant that happens with the tissues, there's a lot of pain, there's a lot of debris which is present. And so that's one of the reasons why I think we have to think about ways in which we can design these implant surfaces so that they have a good interaction with with the tissue, and that's what one of our focus has been. As a matter of fact, the current implants which exist in market, they do have surface modification. There's already a surface modification which is present. There's different things which are done. So for example, you will have some micro machining to make it porous. You could do sandblasting, you could do etching, you could do plasma treatment. There's a lot of things that are already done to a lot of these implants, not just from the texture, but also from the chemistry, because hydroxyapatite is very commonly used as a coating for these kind of implants. And these are commercial products. So there are a lot of commercial products which are actually made uh, using these kind of techniques which are there. But one of the things which is really important and that is missing in some of these is it does not really represent the bone tissue. Remember a few slides back I talked about the bone tissue and the ECM and the cells and the properties of ECM. A lot of these modifications which are used, they are not really relevant in a sense that they don't replicate the features of tissue. So if you think about bone, it's a very big tissue in our body. But if you start thinking about the components of bone, how bone is actually bone is actually built using nanomaterials. It is actually built using collagen and it is built using hydroxyapatite, and these are nanomaterials. There are nanofibers which are made from collagen present in the bone, and they have pores. The pores sometimes are large, sometimes they are small. And so you have this very interesting architecture of the bone tissue. That is what's missing in the existing implants. Existing implants do not have the same kind of features. And so our goal is that how can we take existing implant and then how can we modify the surface so that it does have these kind of micro nano features. It could be a hip implant, it could be a screw, it could be a scaffold. All of these type of metallic implants, how can we now use some techniques to improve the surface properties so that now when these implants will come in contact with the bone, because the implant surface has similar properties like that of the bone, there's a good interaction. The cells from the bone will go on the implant surface, grow the new bone, and they would just tighten that implant, and you don't have any chance of loosening of that implant. And so that's what our goal has been. And for many years, we have actually used a very simple technique, which is called anodization. This is a technique where we actually take titanium and we anodize the titanium in an electrolyte using a cathode. We use platinum as a cathode, and we can do some really interesting things. So you have a titanium surface, very plain. You can see grain boundaries and things like that. But when you start doing this anodization process, you start seeing these kind of surfaces. These are not deposited; these are growing from the surface. So you grow these kind of nanotube structures from the surface. And what this does is that now you have a flat surface. Obviously, you change the surface area, but you also now have actually a very different topography. It's a nanoscale topography because these tubes are nano in size, and depending on the what voltage we use for this, we can get different sizes of nanotubes. Depending on what electrolyte we use, we can actually get different space. So for example, if you use a different kind of electrolyte, you can have all the tubes touch each other. or you can have all the tubes which are far apart. So you have some control over the topography. And what this does, what is the difference between these two, is they have very different surface energies. So when you put a cell on a surface like this versus a surface like this, the cells are going to know exactly that this is very different than this, and they will have a very different performance. So you have some control of what kind of surfaces, what kind of cell response is going to happen from these surfaces. So this is a very simple technique. For many years we have done that. We normally use titanium, but we can do this on many different types of alloys, and we have done with many different types of alloys that Dr. Ana Paula, Professor Ana Paula makes it. We use some of these materials, and we can also do these kind of nanostructures on these. The biggest advantage of these kind of surfaces that they're actually hydrophilic. So you have titanium, which is also hydrophilic, but as soon as you make nanotubes, what you find out is that the contact angle is less than 10. So it's a very hydrophilic, very high surface energy. And the interesting thing about this is that now when you have cells that come on the surface, they can spread. When you have protein that comes on the surface, it can actually spread, and that is really important eventually for the integration of the implant with the tissue. So it's actually very important to have that. A lot of our work has been looking at how mesenchymal stem cells will interact with these surfaces. So what we do is we take the mesenchymal stem cells either from the bone marrow or from the adipose tissue, from the fat tissue. We put the cells on these surfaces, and then we see what happens to the cells. Are the cells able to spread? Are they able to grow? And we consistently find out that with nanotubes, we have much better cell growth. This is a fluorescence microscopy images. All the blue dots that you see is the nuclei. All the red that you see is the cytoskeleton of the cells. These are actually the mesenchymal stem cells from the adipose tissue, from the fat tissue. And as you can see that on titanium, it is okay. Titanium is not a bad material. But then when you create this nanotube surface, you have a very significant difference which happens. And this kind of carries over. This is an SCM image which shows how the cells are, they're all interacting with each other. And what we find out is that when we start growing these cells for a long period of time, we see that these cells are producing the proteins which are part of the bone, which is important. So at this point, you can see that the number of cells are all the same. Everything is covered. But these cells on these surface nanotube have a lot more green dots. And this green dot represents a specific protein, which is called osteocalcin. And this osteocalcin protein is the one which is really, really critical for the health of the bone. So if you see osteocalcin is produced on the surface, that means the cells are happy, and eventually the cells will grow new bone, and in that way you have a good binding that's going to actually happen. Now, this is good, all fine, but how can we make this better? And I think we have used some other types of methods to make it better. So one of the methods that we are using right now is this polyelectrolyte multilayers. We are doing biomolecular modification, where we take these nanotubes and then we build layer by layer assembly of anion, cation. And we use this anion cation, which has some biological function. So we are actually using things like heparin, chitosan, hyaluronan, tenflock. Tenflock is a very interesting material because it's derived from tannin, and this tenflock, is a material that is very underutilized, and so I think we wanted to see if the tenflock is going to have some effect or not. And so we create these kind of surfaces. Again, SEM images just show that when we do this modification, we can still make sure there is nanotubes, because we don't have nanotubes, it is of no use. You do need to have nanotubes on the surface. And then, as I mentioned, tenflock, is a very interesting material. It has good biocompatibility. It is not toxic. It also has antimicrobial activity. And so I think that also makes it a little bit exciting. And what we find out is that as soon as you put tenflock, you have a lot of bone deposition. You can see there's so much green. Now it's very interesting. When you have tenflock with heparin, we have a lot. But when you have tenflock with hyaluronate, we didn't have a lot. And we expected heparin is going to work because heparin has certain signaling factors that help. But this is something which is very interesting for us, that we know nanotubes are good, but if you modify these nanotubes, we can make them even better. We can make their performance even better. We've also done some bioglass modification. This is actually in collaboration with with Dr. Giulietta Rao from Italy. They actually deposit bioglass on these nanotube surfaces. These bioglasses, they have manganese. Manganese, has some activity. And what we find out is that we can still maintain the structure of the surfaces, but when we start doing the cells, we find out that there is even uh, better differentiation of cells is happening. See, the important part is that when you have an implant comes at the bone, you want the cells to come to the implant. You want the cells to attach, you want the cells to actually grow, and then eventually you want the cells to make bone so that you have good bonding. And so everything that we do, we want to actually see what is happening to the cells in the late stage. So what happens after 1 month? What happens after 14 days? And we find out that bioglass is actually very potent in terms of making sure the cells will start growing bone. Now, we don't really see the bone grow because we are not doing studies inside the body. All the studies are outside the body. They're all in vitro. But this protein is the one that actually tells us that eventually the bone is going to be formed. It's a marker protein. It's a very important protein that helps in making sure that the cells are healthy and they're doing what they're actually supposed to do. So again, you can see here in 14 days, you have the cells, and you can see the cells here. You can see the nanotube, but in 28 days, the whole surface is colored. And we also start seeing these kind of nodules, which are actually hydroxyapatite, which is being produced by the cells. We do see that on nanotubes because we know nanotubes are good, but we know that on the bioglass we have a lot more of these. So, and what that means is that these implants will integrate faster, which means patient will heal faster because you have a much faster interaction that happens. Let me change the focus a little bit and talk about cardiovascular applications. We have focused quite a bit on cardiovascular implants because it's actually one of the leading causes of death. A lot of people die, and we spend a lot of money in making sure that people still live healthy life. So once the damage has happened, you cannot change the damage; it's permanent. But how to make sure that people can live healthy lives is the focus. Here is a map, and again, I don't have a map for Brazil. This is just for United States, and you can see that the darker the color, more people have cardiovascular disease. And you can see that some parts of the United States is very, very bad in terms of heart disease because it's based on the diet, based on the lifestyle. There's a lot of things that affect the cardiovascular health. Well, just to give you an idea, Colorado is in this area, and Colorado has a very active lifestyle. People are very active. They do a lot of hiking, jogging, running. So we have very less. But a lot of the states here, like Texas and all these states, they have actually very different lifestyles, very different eating habits, and so you have a lot more cardiovascular disease in those areas. And everything that we do right now in cardiovascular disease is to make sure the damage doesn't increase. We cannot completely reverse the damage. So it's a very important area where you want to make sure that people who have some disease, they are actually going to be able to live healthy, by putting medical devices. And a lot of these diseases, they're either because of heart or because of blood vessels. So, I'm going to talk mostly about the blood vessel related. So normally blood vessels are the ones that carry blood in every part of our body. And many times because of certain kind of environmental conditions like the food and everything, what you see is that you'll have some deposits that would happen. So you have a blood that flows in healthy people, but you can have some deposits and the vessel becomes a layer. What it means is that it's going to now exert pressure on the heart and people can have heart attack. Sometimes you actually can have this clog lift and start flowing in the blood. That is also very bad because then people will die very quickly when something like that happens. This kind of disease is called atherosclerosis, and this is not something that only affects the heart. It can be any part of the body. A lot of people get this in their legs. In the blood vessel in the leg is where they have a clot, and that is then going to affect the heart, and the people will die because of heart attack. And so this is something which is very important and needs to be taken care of very quickly. The treatment for this disease is either you can actually do something called angioplasty. Angioplasty is where you can put a stent, and the stent is a tube made up of a wire, and that tube will make sure it opens so the blood can flow and it won't have any problem with clogging. Or you can do bypass. Now, angioplasty is very straightforward. People go in the morning, next day in the morning you can go home from the hospital. Bypass is a very big deal because then you are going to be in the hospital for many, many days, maybe a few weeks, because they have to literally open up your chest cut the damaged part, take something from different part of the body, put it there, or put a vascular graft, and that is a very involved surgery. So doctors always try to do the stent first, and if this is not an option, then only they'll do bypass. I'm going to talk about stent today because stents are actually made from titanium alloy. Stents are actually made from an alloy which is called nitinol, nickel titanium. And here is a picture of what is stent. It is a wire tube mesh that is put in the blood vessel using minimal invasive surgery, using a balloon system. It is made from nitinol, so it is a shape memory. So when you put it in, you can open up the shape. So you can make a very small hole, put the stent, and once it reaches the place, you open it up so it actually takes the shape. Vascular stents, there are two types. You have the bare metal stent. The bare metal stent means it has no coating on it, just metal. Or you have a coated stents or drug-eluting stents where there is a polymer coating and the polymer actually has some drug in it. So slowly the drug is coming out. And I'll tell you what is the reason and why we would choose this or that kind of a stent. And so with a lot of these stents, if you have a bare metal stent, you will put the stent, but after some time, the stent is going to irritate the tissue here. The stent is going to irritate the tissue, and the tissue will start growing, and then the tissue will grow and apply pressure. And in that way now, the whole reason you put the stent is the reason now, same reason is happening again, which is called restenosis. To prevent this, we can have drug-eluting stents. Drug-eluting stents are the ones which release the drug so they can stop this from happening. But once all the drug has come out, you have the coating, which is very uneven now because some coating has come out, some coating has not, and then you have blood clotting that's actually going to happen. So you have blood clotting that happens, which is called thrombosis. So both of these types of stents have some issues, and we need to figure out what to do with these stents. There's some very interesting interaction that happens, and I won't go into a lot of detail about this. So especially when blood comes in contact with the surface, you have protein adsorption, you have platelet activation, and then you have clotting that happens. But you can also have inflammation that can go on, and that can also regenerate that. You can also have vascular injury. The vascular injury is typically where you have restenosis that's going to go on. So all of these are actually happening because of interaction of the material with the surface. If you have the right material surface, you can prevent all of these things from happening, and you have a good integration that happens. So that's one of the goals that we have had. So again, we have used these nanotube arrays for stents. So our goal has been that take the stent and create these nanotubes. And nanotubes are hollow, so we can put some drugs in it. But the reason why we think nanotubes are good, because if you look at the blood vessel and the inside of the blood vessel, you have a texture that looks like this. You have this hair-like structure that is actually present. This hair-like structure is called endothelial glycocalyx. It is a nano structure. So our nanotubes, they look like this. The only difference is that the hair-like structure is very flexible. Nanotubes are very rigid. But that is okay because you can have a flexible structure with a stent because the stent will collapse. So the only disadvantage of these nanotubes is that they're very rigid. They're not flexible like endothelial glycocalyx, but the size is exactly the same. We have very similar size, which is there. And so we have done a lot of work with blood. We go to the blood bank and then we take some blood, and from the blood we remove the plasma, and then we put the plasma on these materials. And what we find out is that now, if you have nanotubes, you have very less adhesion on the cells. Here we want less cells to adhere because less cells means less clotting. You can see in this picture here, the big round here is a white blood cell. The small ones are platelets. And when the platelets and white blood cells do like this, that is the first step of blood clotting. Eventually, then the blood clotting will happen. And then you'll have a lot of problems which will be there. We can prevent those kind of things happening by creating this nanostructure. We have also done a lot of work with blood clotting, so we can actually put a drop of blood on it and allow the blood to clot and see how the blood is clotting, and we can look at the kinetics of blood clotting, and we find out that with nanotubes, we have slower rate at which the blood is actually clotting. We have also done some work with foreign body reaction, because normally what happens is blood clotting is one thing. But if blood clotting doesn't happen, and if you have the inflammation that happens because you have white blood cells, these white blood cells can then keep on doing multiple different processes, and then eventually they form something called foreign body giant cells. And these foreign body giant cells will start the rejection cascades. It is not clotting, but it's another type of rejection that basically happens. And we can see foreign body giant cells on titanium because you can see a lot of cells are clustered and you have a lot of cell nuclei. Here we have minimized these as well. Now, all of these are good. We have good results, but they're not best. And so our goal has been how can we make it better? And so we thought that maybe the 10-flock heparin that we had developed for orthopedic application might work because heparin we know that it actually prevents blood clotting, but we also know that 10-flock has some really interesting biological properties. And so what we did is then we created those polyelectronic multilayers and then we put some plasma on these surfaces. And what we find out is that especially with chitosan and heparin and chitosan and hyaluronan, it was really, really bad. This is actually controlled. You see that is happening. But actually, if you do chitosan heparin and chitosan hyaluronan, it's even worse. But as soon as we use 10-flock heparin, we saw significant reduction. Now, here we made different layers, 19 versus 5 layers, just to see what happens to these layers. It didn't make a lot of difference to have more layers because the less number of layers were much better. 10-flock hyaluronan was actually not as bad as these chitosan one, but it was not great as well. So we thought that this 10-flock heparin is something which is very, very interesting. The next thing that we also did is we actually tried to put nitric oxide on the surface. Nitric oxide is very interesting because in our blood vessel, nitric oxide is releasing all the time in our blood, which also helps in preventing the blood clotting. And so we developed some chemistry techniques using these polyelectronic multilayers where we put nitric oxide in it and slowly, nitric oxide release so it actually prevents the blood clotting from actually happening. And so we have developed this chemistry and we've also looked at how the nitric oxide is releasing. You can see that when we do this method, we can still see the nanotubes. We are not blocking all the nanotubes here. And then you can see that you have this release of nitric oxide that happens. Nitric oxide comes very quickly. We don't want this. We want nitric oxide to come for many, many hours. But this was the first step that we wanted to make sure and see that how the nitric oxide is actually coming. And the most interesting part was that when we had nitric oxide, we practically removed any blood clotting. We did not see any kind of platelet or white blood cells on the surface, which was actually pretty exciting. So you can see a lot of platelets when you have titanium, and you see a lot of platelets when you have nanotubes, but as soon as you have nitric oxide, practically everything is gone on the surface. We want a surface like this because it is not going to clot, and you won't have blood clotting problems. One other approach has been to use super hydrophobic surfaces. So everyone probably has seen a lotus leaf, and the lotus leaf effect is where the drop of water remains a drop of water and it just slides off. So we thought, can we use this approach? The reason why this approach works really well is because you have a texture on the surface. There is a texture, but there is a chemistry. So we have a chemistry and texture on the surface. So we thought that we can create textures. We know that. To create chemistries, maybe we can use a carbon fluorine bond because we know Teflon is very hydrophobic. So if you combine the CF bond with the textures that we create, can we create super hydrophobicity or not? And so what we found out, and I won't talk into the detail of the theory of super hydrophobicity, that has to do a lot with Cassie-Baxter state, where you actually trap the air in the texture of the surface because you have a chemistry and the drop of liquid remains a drop of liquid. But here are some pictures. You can see this is blood. This is plasma, and this is water. These are drops on titanium nanotube surfaces that have this super hydrophobic coating on it. And you can see that it's very much like a drop, it doesn't spread. I will show you some pictures afterwards where you will see the spreading that's going to happen. But because it's a super hydrophobic surface, nothing is going to attach on the surface. Nothing is going to remain on the surface. We can still control, the surface looks exactly the same. And you can see some videos here. So this is titanium, you can see the drop of water. It remains as a drop of water. This is nanotubes. You can see the drop of water spread because we know that it's hydrophilic surface. This is titanium with the treatment. We use silane treatment, so you can see that it is hydrophobic. But look at this video here, which is a nanotube with silane, which is super hydrophobic. It's a slow motion video, and you can kind of see that the drop of water just bounces, off. So imagine that if the liquid is flowing on the surface, it would just slide. It is not going to stick like this, or like this on the surface. And that would be good because then you can prevent blood clotting from happening. So we have done a lot of work looking at interaction of blood. We have done a lot of studies where we are trying to see how blood is interacting. So we have fibrinogen adsorption, albumin adsorption, factor 12. We consistently find out that the superhydrophobic surfaces are going to be much lower in all these protein adsorption. And when we do the platelet interaction, what we find out is that we can also prevent a lot of platelets from adhering to the surface. I have some more videos as well to show you. This is some blood clotting. So as I said, you can take a surface and put a drop of blood and allow the blood to clot. And what we find out is that there is no blood clotting when we have superhydrophobic. There's a lot of blood clotting which is going to be there when we have non-superhydrophobic surface. But these are the exciting videos that I want to actually show. So as you can see here, this is a surface of titanium, and this is real blood, human blood, and you can see that how the blood is spreading. And now if the blood was flowing, it is going to stick on the surface. You will see that the blood is actually going to stick on the surface, and here is where the blood clotting is going to happen. If you actually have nanotubes, what you find out is that uh, it is spreading on the surface. And you can see that when this is lifted a little bit, uh, see how all the blood is actually coming out. So a lot of blood comes out, but some blood is also going to stick. This is one type of superhydrophobic surface. You can see how the blood is bubbling up. It is not spreading because it's a superhydrophobic surface. Um, and you can kind of see what is happening now when the student is lifting the surface. Uh, all the blood just comes out. Everything just is removed. And this is the best one because this condition was the best one where you can see that the blood doesn't want to stay on the surface. Nothing happens on the surface. By itself, it just goes away. You don't even have to lift the surface. And so I think that is what our intention is, that we don't want blood to interact with the surface, so there is no clotting, that's going to happen. Uh, we have also worked on antibacterial surface. I think I have a few more minutes, so I'll talk about antibacterial surface. We have done a lot of work on antibacterial surface. One of the goal is to prevent infection on implants. Infection on implant is very bad because if you have infection on implants, you have to take the whole implant out, do some procedure, and put a new implant, and that is very, very complicated. And if the bacteria biofilm that you have detaches and goes in the body, you can have sepsis. It can be really, really bad. And so our goal is to actually allow the cells to adhere, but prevent the bacteria to adhere. And so we have done some work specifically related to that, and we have looked at different types of bacteria. Especially the S. aureus and the Pseudomonas aeruginosa are very critical for orthopedic applications. These are the bacteria which are involved in infection of orthopedic implants. And one of the things is that a lot of gram-negative bacteria, we don't have good antibiotics for it. Gram-positive, manageable. But gram-negative, it's not really manageable. So we wanted to see specifically if we can reduce the adhesion of gram-negative bacteria. And so we have done some work with both polyelectrolyte multilayers as well as superhydrophobic surface. Polyelectrolyte multilayers again were very good because we know that 10-flock has antibacterial properties. What we found out was that with 10-flock heparin and 10-flock hyaluron. So here it was opposite. If you remember with platelets, 10-flock heparin was good. Here 10-flock hyaluron was good. But we know that 10-flock is a common thing. And so we want to continue keep on exploring that. And we find out practically no bacteria on 10-flock heparin. The whole surface was completely antibacterial with the nanotubes. Without the nanotubes, yeah, you will have some bacteria which would be there, but with the 10 flock and hyaluronan, I think it was one of the best. And the same thing what we found out was with so this one was with gram negative, which is what we were very interested with. This is with gram positive, which was okay. We still could see that gram positive was not as great, and we are trying to figure out how we can now reduce gram positive as well. Gram positive antibacterial antibiotics work better. Now that is not the reason why we shouldn't work on this. We should still work on this because we would want nothing to attach on the surface. So a lot of our future work right now has been on looking at the 10 flock mechanism of action. How can we actually understand the mechanisms of TenFlock and make it better, so we can actually have better response. We are also trying to work more on the super hydrophobic surfaces. And one of the things about super hydrophobic surface is nothing is going to stick on the surface. Everything is going to not attach, which is bad because we want cells to attach, but bacteria to not attach, blood to not clot. So we're trying to figure out some combination of super hydrophobic surfaces with cell adhesive surface. We have also used different types of methods. So we are actually using some plasma methods, some ion deposition methods, some hydrothermal treatment to make textures. We are also looking at red blood cell interaction with surfaces. Red blood cell interaction is important because whenever we talk about blood clot, we always talk about platelets, and we talk about uh, white blood cells and proteins, but we never talk about red blood cells because they're a very important part of clotting. So we are looking at red blood cells. We are also trying to do some animal studies with the cardiovascular area. Our next step is to look at endothelialization and smooth muscle cell interaction, because those are the two cells present in the blood vessel. We know about the blood clotting now. We want to see about the cells and how cells actually interact. So this is some of the work that we are continuing to do in my lab. And so just to summarize, I think my lab is very multidisciplinary. I work with a lot of people in different areas. We do a lot of materials engineering work because we don't make new materials. We have excellent collaborators who make materials, but we actually engineer these materials so that we can study biological interactions. And we use nano surfaces, nano texturizing techniques, because that allows us to make surfaces which are more similar to the kind of tissues and the properties that the tissues have. And so our work is in this area here, intersection of nanotechnology, materials engineering, and biological interactions. With this, I really appreciate this opportunity to talk about my work. I hope that many of you who are watching are interested in it. I'm very happy always to collaborate, also host students from Brazil for sandwich PhD, or even a short-term project. I have hosted many students from Professor Ana Paula's lab over many years. I think a lot of these students, they come and they do a lot of work, and we have a lot of publications. I think that is very important for us to have collaborative projects, because all the projects that I talked about, all the things that I talked about today, a lot of these problems are very global problems. All the people in all across the world have cardiovascular disease, have orthopedic implants. And so I think it is very important to uh, develop surfaces, develop technologies, and work in collaboration, with different faculty. So I hope that I have given very brief background about our research. I'm always very happy to talk to students and postdocs and other researchers and professors, and discuss more about collaborative projects to work on. With that, thank you so much, Professor Raphael, for inviting me. Thank you very much to Professor Ana Paula for introducing me to you. I'm happy to answer if there are any questions.
Thank you. Thank you very much, Professor Ketu. It's amazing talking, very amazing. And before I start here with some questions, I also would like to kind of joke, because I love when my field of research is completely different. I'm work with superconductors and perhaps ceramic materials. But when I saw on those presentations and I saw tannins, I realized how important it's it's to drink red wine. So this makes me very happy. But it's just a joke. Uh, I have here some questions of our students. They are, thank you for the nice presentation, and also Luis Rogério are asking about bioblasts and the use in orthopedic implants.
Yeah, certainly. Bioglass is very interesting because, people were so excited about bioglass many years back when it was actually discovered. And suddenly then it kind of went down, and I think it's slowly coming back. I think it's like a forgotten material, I feel like. I think it has some really interesting bioactivity with the cells, especially in terms of making these cells function faster so that you have faster healing. So there is a potential of being them used for pretty much any type of orthopedic implants. I think that the thing about bioglass is going to be the ability to control the surface in a more appropriate way, ability to present bioglass in a very controlled way, so that when you have the cells that see the surface, the cells are going to be able to do the function, and you don't have uneven behavior of the cells. I think that's going to be the most critical.
Oh, nice. Uh, Also, Luis, no, I pressed the wrong place here. What's your opinion about polymer applied in medicine?
I think a lot of our tissues, we will have to use polymers. Polymers are very interesting in a way because you have much more tunability, right? With metals and alloys, I think the mechanical properties tunability is limited up to a certain extent. But with polymers, you have very flexible tunability in terms of mechanical properties, in terms of making them softer, making them hydrogels, making them more tougher, controlling their degradation. Because when you control the degradation, you are going to have different uh, applications like drug delivery and things like that. So I think polymers are very, very important. I think they're going to be very critical. The biggest part about polymers that we all have to think about is, what if the polymer is degrading, are the degradation products toxic? What is long-term toxicity? With metals and things like that, there is toxicity as well because you have ion leaching and things like that happen. But metals have been used way before polymers have been used. We know a lot more about metals and how metals interact with human body. With polymers, I think as we discover new polymers, as we make new polymers, I think we'll have to be very careful about the degradation, the toxicity of the degradation products, the stability. Many times there are polymers that you put inside the body, and then very quickly they actually lose the mechanical properties. So the mechanical integrity of the polymer is going to be very important.
Wow, nice. It's interesting. The polymer PDP, polyvinyl dihydrogen, was used in the Second World War as a blood plasma, so to
Yeah, yeah, yeah,
substitutes. It's kind of amazing
yeah,
thing. And now it's a good
yeah,
polymer to produce nanomaterials, metallic nanomaterials, uh,
yeah,
because some properties of this polymer. It's very, very, very
yeah.
interesting. I would like to make, I think, one or two uh, questions, only for curiosity. I'm not working at this area, but my mom, she has osteoporosis. So I was asking how an implant, a bone implant, could work with people that has this kind of disease, because I don't know how it works.
That's a very interesting. So osteoporosis is very complicated because your bone is becoming porous, right? I think when you have arthritis, I think the implants make more sense because arthritis is where your cartilage is lost and your bone is rubbing, so you have pain. So that's why you put a joint, and then you can
Mhm.
relieve the pain in that way. I think osteoporosis is porosity, bone, and especially women after menopause. A lot of them, because of hormonal changes, get osteoporosis. A lot of the people that work in the area of osteoporosis, they are looking at some drug delivery, and that is where some polymers and nanoparticles of polymers come, because you can inject these nanoparticles with some drugs into the bone, and that allows the bone to regrow and you know make the bone less porous. I think implants would be very difficult to use for osteoporosis because the bones are so soft. They're very porous. So I think it's very complicated to use implants. But there's a lot of people who work on the drug delivery aspect. Nanoparticles and drugs that you can target inside the bone. A lot of the drugs that you take right now are oral or injections, and it takes a long time for them to reach the bone and be effective. Sometimes they give injections in the bone for that reason, so that you can stimulate the growth, but you still don't have a good way of locally delivering the drug. It just disperses everywhere, and only maybe less than 5% of what you give is really working.
Okay.
So a lot of the work in drug delivery is how we can target drug delivery, how we can control the drug, and how we can focus the drug. So in that way, it is more effective.
I see. Thank you. Thank you very much. I have one more question here from Caio. Thank you, Professor Ketu, for your excellent class and congratulations for your work. Would it be possible to have different surface tuning in the same implant?
That is, yeah. And as a matter of fact, existing orthopedic implants, if you look at a hip implant, you have certain parts of the implant which have surface properties, right? Some part are smooth, some part have porosity, some part have roughness. And I think we will have to do that. We won't be taking the whole implant and making
Mm-hmm.
it, because there are certain parts of the implant where you need that good bonding. And that's where you would have to do that. And so then this becomes a very interesting mechanical engineering problem, right? How do you come up with manufacturing techniques to actually create different textures on different surfaces in a very industrial process, and so yeah, absolutely, I think we will have to do uh, different types of surface chemistry, surface topography in different parts of the implant.
Nice. And just to finish, I would like to make this question too about magnetic materials because some time ago, I think 4 years ago, I was with Ana Paula in Grenoble, so, I think so. And I saw a presentation that they are using some magnetic materials to, and these cells are moving as due to this interaction with magnetic field. And for me as a physicist, it's quite impossible to imagine an interaction between magnetic property, a magnetic field, and a cell. Do you
Yeah,
already work with something related or?
we we have not worked with the magnetic materials, but I when I teach a class in biomaterials, I talk a lot about magnetic materials, because especially nanoparticles, right? Nanoparticles are small enough so the cells can actually ingest those particles, and then based on the magnetic field, now you are actually forcing the cells to move
I
in one direction, you know which
Mm,
is important. In our body, when we are healthy, our cells move around. There's a lot of cell migration that happens. But when you have a disease or when you have a damage, cells don't do that, and they don't do the repair. So magnetic field is a way for cells to get encouraged, and you can direct them in certain ways. So they use these super ferritic, iron-based iron oxide nanoparticles that are very small, 10 nanometers. Cells are about 10 microns,
yes.
so the nanoparticles can go inside the cell, and then you can use magnetic field to guide the cells
Oh,
to
nice,
different
nice.
parts of the body.
Very engineering. Yeah, very
Yeah.
nice. Nice. Let I see. I think Kyle wrote here something, but I think you already answered. So, Professor Ketu, thank you very much once again, and I wish you a good congress and also a good trip because
Thank you.
you will stay here in Brazil for a while. Am I right?
No, I go back on Sunday.
On
Yeah,
Sunday,
on
okay.
Sunday. On Sunday.
So have a good trip back to US.
Yeah. Thank you, thank you. And hopefully next time when I come back to Brazil, I can come and visit in person to on and
Of
meet more
course. You
people.
and Anna has to come here in the
Yeah,
Solteira to visit
yeah,
us.
yeah.
Thank you very much.
Thank you very much. It was very nice to meet you in virtually meet you, and thank you very much for giving
It
the
was a
opportunity to talk about my research.
it was a pleasure. Uh, bye bye, Ketu.
Thank you.
See
Thank you.
you
Bye.
around. Bye bye. Bye bye, guys. Thank you to watching us. Bye bye.